Vertical circles are a different ball game altogether. And they're different because now gravity comes into play. Whereas in horizontal circles, gravity doesn't come into the equation, but in vertical circles it does. And but before you do that, you should go to YouTube and Google coat hanger balancing trick and just watch this video here on this guy here. The unfortunate thing about our present situation is you miss me doing this trick, and I sort of mastered it over the years. It's a great trick, and it really works. It's basically spinning a penny on a coat hanger, and as long as you spin it fast enough, that penny will not fall off. So even when it's upside down, the penny won't fall off. So watch that video, and hopefully it'll pique your interest in vertical circular motion. Here are the considerations in your notes you've got to consider. So you can read all these notes, but let's just go right down to the diagram here. So here's something moving in circular motion, and here are all the forces acting on it and the directions of those forces. And it depends on the situation. If you're talking about, let's say, a roller coaster, or you're talking about spinning, if you've got an object on the end of this string and you're spinning that in a vertical circle. And that's why over here we have normal force or force of tension. So if you're sitting in a roller coaster and you're going around the circle and you go upside down, so at this point you're upside down, and you're talking about the normal force. But if you've got a weight on a string, and you're spinning it in a vertical circle, then you're talking about the force of tension. So this is a normal force problem, and this is a force of tension. But look at the direction that the forces are pointing. So for example, if we go to the bottom of the circle here, everything's the centripetal force is pointing towards the center of the circle, because the centripetal force will always point towards the center of the circle. The normal force is pointing up, and the force of gravity is pointing down, right? Or the tension is pointing up. If you go to the top of the circle, then this is where it gets interesting, because at that point, everything seems to be pointing down. So you ask yourself, well, how did that penny stay, if you're spinning around a circle, how did it stay on the end of the coat hanger when you're spinning it around a circle when it's at the top here, if all the forces are pointing down? And the same applies to this roller coaster. Roller coasters, theoretically, do not need to be the carts do not need to be attached to the track in any way when it's at the top. As long as it goes at a great enough velocity, this cart will stay on the track, even if it is not attached to the track in any way whatsoever. It's on the rails, obviously, but nothing's holding it from falling down. And we'll discuss that more as we go through these problems. So just take a note of this little chart here. And let's go right to one of the problems. So here's our classic problem. Example 2, we're going to do an A and a B part to it. I think we're going to do an A and a B. Yes, we are. So don't take up too much space for your A. Let's split it in two. And here we have a roller coaster going through a loop that has a radius of 4.8 meters. The roller coaster car is at a speed of 13.8 at the top of the loop. During testing and development of the roller coaster, it was determined that the cars and passengers have a combined mass of 4,800 kilograms on an average run. Determine the amount of force the track must be designed to withstand at the top in order to keep the cars going around the loop. Okay, so here's a circle. Here's the car. It's at the top of the loop. And just think about this problem before you solve it. Ask yourself, is there going to be more force if this car is going around the circle at a constant velocity? Is there going to be more force at the top or at the bottom, or is it going to be the same force? And the answer is clearly there's going to be less force at the top, because gravity's pulling it down. Gravity's pulling it away from the track, where at the bottom, when you have the car on the bottom, gravity's pulling it into the track. Plus, as the car goes around in a circle, as it comes around here, it's putting a huge amount of force on the track. So the track actually has to be the strongest at the bottom, and it can be the weakest at the top. Of course, if you're designing this, you're going to want it to be strong consistently strong throughout, but just as a physics principle, the least amount of force is going to be at the top, and the most amount of force is going to be at the bottom. Okay, so at the top, what's happening in terms of the forces? Well, the force of gravity is going down. The normal force, that's the normal force, the track is pushing the car down. And the combination of those forces is the centripetal force, which is always towards the center of the circle. So it's also down. So in other words, the signs of these three forces are all either negative or all positive. Let's just call them all positive so that we don't have a ridiculous amount of negative signs. What's causing the centripetal force here? It is the normal force and the force of gravity. So this is how we write our equation for vertical problems. We write the centripetal force equals normal force plus the force of gravity. And what is the question asking us to solve? It's saying what force must the track be designed to withstand? So what force is that? That's the normal force. It's asking us to solve for the normal force. Normal force equals the centripetal force minus the force of gravity. Continuing on, the centripetal force can be expressed as mv squared. The gravitational force can be expressed as mg. And you'll notice in this problem, as opposed to our horizontal circular motion problem, the mass is relevant, which makes sense too, doesn't it? If you have something of 5 kilograms going around this track, the track is gonna have to be have far less strength than if you have something in this problem of 4,800 kilograms. So the mass is relevant here in this specific question. And then we can just plug the numbers in. 4,800, what was the velocity? The velocity was 13.8 squared. Oopsie. Again. Squared divided by the radius, which is 4.8, minus the mass, oops, I don't have a space here, over, times gravity. Now we have to be careful here. Is gravity in this case going to be positive or negative? Well, we already said in this problem, the signs of all of these are all going in the same direction. So if I designated this one here, this FC, if I've designated, I have no negatives in there. If I've designated that as being positive, then I must also designate gravity as being positive. And that's why I'm putting a positive 9.81, not a negative. And you'll see when we do our part B problem here why that's important. So you stick all that in and you end up getting an answer of 1.43 times 10 to the 5 newtons. Part B. So part B is going to be the same question, but this time we're going to determine what force is going to be experienced at the bottom. So at the bottom. And if we just draw our three forces here, Fn is going up. Fc is going up because Fc is always towards the center of the circle. This time Fg is going down. So now we have two of the forces going up and one going down. And the problem is identical to A. So we're just solving for Fn. Oops. Sorry about the messiness and running out of room here. This time we have to be very careful because Fg is going, if I'm saying that Fc is going up and is positive, Fg is going down, so now I'm going to have to put that negative back in there. Is it 4,800? Oh, just fit it in. And as you can see, that is going to have an effect. You have a negative and a negative, so that's going to become positive. So you're actually going to end up adding these two numbers. And that's what you get for your answer. So as you can see, there's almost twice as much force at the bottom than there is at the top, which intuitively should make sense to you. Okay, we got two more problems. We're gonna get, let's just barrel through these other two problems. This is the most interesting one. Is this next one? This next one says example number 3: determine the minimum speed. The minimum speed, very important. Determine the minimum speed the cars on this roller coaster can move in order to just barely make it through the loop at the top. So they're at the top. Now what happens, and again, think about this in your head. This is a thought experiment. It's very important in physics. You're going around this track. You're going around super fast. When you get to the top, you're going to feel a lot of force pushing you up into the track, right? And that's why I didn't need to even explain that. That's why you're not going to fall. You're not going to fall down, or this car is not going to fall, because when you're going really fast, you have, when this is high, your velocity, when it's really high, you have a great amount of centripetal force. The centripetal force is towards the center of the circle, but there's going to be an equal and opposite reaction pushing you up this way. So the faster you go, the more you get pushed up into the track. You're going around really fast, you're getting pushed up, you start to slow down. What are you going to feel? What are you going to feel? You're going to feel less and less pushed up into the track, or less pushed up into your seat, in fact. And if you keep slowing it down, keep going slow, eventually the gravitational force will win and the car will fall, and you will fall if you're not somehow attached to the track. So we're going to determine what's the slowest you can go, where this physics principle will hold, and you will keep going around in a loop. Same problem as before. We got FC. Let's just FC is going down, FG going down, FN going down. But you have to ask yourself, if I keep slowing down, as I said, I feel less and less FN, right? The track is pushing me down to the center of the circle less and less. And for the minimum speed, your FN becomes 0. So if your FN is 0, when I plug it into my equation here, if that's 0, I'm just left with this. The centripetal force equals the gravitational force. mv squared over r equals mg. And you shouldn't be surprised, but you will. What cancels out? What becomes irrelevant in this problem? Once again, the mass becomes irrelevant in this problem. Or else again, they'd have to design, when they design these roller coasters, they'd have to design for every different mass you could think of. For the objects going around in circles. So the mass becomes irrelevant, and then if you solve this formula for, now what's the question asking? I forgot. Determine the minimum speed. Velocity squared equals rg. That's it. This whole question boils down to that one simple formula. The velocity equals the square root of rg, because the masses become irrelevant. Square root of r, which was 4.8 g, 9.81. Forget the negative. It's irrelevant. And you're going to get an answer of 6.86 meters per second. That's the slowest the car can go around and stay on the track. Any slower than that, and once it gets to the top of the track, gravity wins, and you have a very nasty accident. Good. Let's get this last problem done so we finish this. Oh, okay, we've done that already. done that one. We have, this time, we've got a mass spinning on the end of a string. So this time we're talking about tension, the tension in the string. Determine the tension in the string at the top of the mass if it's spinning at that velocity. This is exactly the same, except that you're just replacing Fn with Ft. So I'm not going to go through all the details. Ft now. Oh, I got that backwards. Ft equals Fg minus Fc. No, it doesn't. I got it right the first time. Fc minus Fg. Fc minus Fg. Mv squared over r minus mg at the top. At the top, Ft is going down, Fc is going down, Fg is going down. They all have to have the same signs. Stick the numbers in. You've got the mass, convert it to kilograms. You've got the radius, convert it to meters. You've got the velocity, and I'm not going to do that, but just make sure that this and this have the same sign. So if I was you, I would just not put a negative in for gravity. I'd just put it as a positive 9.81, and you're going to determine that the answer is 20.1 newtons. And that brings us to the close of a long lesson on vertical circular motion.